Today we will begin the study of integration from a numerical analysis perspective. Unlike other modern applied mathematics tools, integration is really quite old and has its roots in something called the methods of exhaustion that was devised at least 2,500 years ago. So we'll discuss some of those basics, and we'll discuss the definition as it's applied today, and we will also look at various methods to improve on the efficiency of integration. So let's first take a look at what we mean by an integral. An integral is really an area. It's defined as the area under a curve between 2 points, which in this picture is depicted by point A and point B. This curve could be positive, it could be negative, and we will do something a little different than what you would normally think of with computing areas. What we will do is define any portion of this curve that is above the x-axis as being positive area, and any portion below the x-axis as being negative area. So when we integrate between 2 points, such as A and B, we will get an accumulation of both positive and negative portions of the area. The integral is denoted through what looks like an elongated S. You might think of that as a summation. And it has two limits, a lower limit we'll call A and an upper limit B. And we will be looking at the area under the F curve, under the function f of x, broken up through differential spacings called dx. If you thought of these dx's as being finite, you could think of these as rectangles, where f of x represents the height of a rectangle, and dx represents some very short width of that rectangle, and the elongated s is adding up those little rectangles. So let's start with an example. This is the integral of the function called the square root of x. And we are going to integrate between points 0 and 1. Well, how would we solve this analytically? Well, if you were in a second quarter calculus class, you would know how to do that. You would view this as x to the 1/2 power. You would take an antiderivative and get 2/3 x to the 3/2. Then you would evaluate that integral between 0 and 1. You'd first plug in 1 into x and get a value. And then you would subtract off the same evaluation at 0 to get a result of 2/3 in this case. So we can do this analytically, but most integrals aren't so easy as this one and require an extra bit of help numerically. So let's see if we can use the definition of an integral to form the area through a method that the ancients would have called the method of exhaustion. The method of exhaustion is devised by using some geometric shape, such as a rectangle, that is made very, very small so as to approximately fit inside of a curve. So those small geometric figures, which in this case are rectangles, are then used to accumulate area, and we will use that as an approximation of the area under a curve. Well, this particular slide shows two such forms of rectangles. One set are yellow and the other set are green. If you focus on the yellow ones, that represents a fairly macro cut at dividing up the square root function into 5 basic rectangles. If you added up the area of those yellow rectangles, you would overestimate the area under the curve. So there's two things you could do to improve that. One would be to narrow the rectangles themselves and make them so there's less loss. And the second thing you could do is perhaps use a different geometric shape that is not shown here on the screen. If we stick with rectangles and we narrow them, you still have a choice of whether you would like the rectangles to sit above the curve or below it. And in this case, the yellow rectangles are so arranged that the right corners of the rectangles are matching exactly the square root function. That forces an overestimate of the integral. If you used the approach of the green rectangles, you would match the left side, the upper left corner of the rectangles with the function, and this would force an underestimate So if you continued to narrow these rectangles, you would approximate that curve better and better, regardless of whether you were coming in from above with the overestimate or coming in from below. So we're going to build a formulaic description of those green rectangles by computing the area of all of them and adding them up separately. So in front of us, we have the width of the rectangle, which is represented by the values of two adjacent points. And we are evaluating the height of the rectangle through the function call at the lower one. So this is clearly the green approach or the green philosophy to this summation. We will then add up all of the rectangles. Well, we'll add up from the basis of the left side of the rectangle. So we're starting with position 0, and we're moving up to the second to last x value because it is the left side of the last rectangle. There are n of these rectangles, and there are n plus 1 points that are describing the n rectangle. We could simplify this a bit by looking at the values x sub k plus 1 minus x sub k and making the requirement that each of those points are evenly spaced. If so, that difference is a constant length, which we could call h. If we did that, we could factor the h out and have a simpler formulation, just adding up the functional values of the first n minus 1 points and multiplying the result by h to give us the same area of these rectangles. Here we have 10 intervals, so we're changing it a bit, and we are characterizing the left side from x0 up to x9 to get our 10 rectangles. We already know that the exact answer is 2/3. We now know that the interval spacing is 0.1, and it's just a matter of calculating the functional values at each point and then multiplying that by h to get the area of each rectangle. Add up the rectangles and you will get a total of 0.61. Now that is clearly lower than the true value, which doesn't surprise us because just geometrically you could see that the green rectangles were producing less area than the actual integral. You could look at it, the error in this case. Generally you can't do error analysis like this because you don't usually know the correct or the exact answer, but here we do. So if we take the computed value of 0.6105 and subtract the true value of 2/3, then we see that there was an error of 0.0562. We already discussed that narrowing the h value or the interval would reduce the error. Let's take a look at how much reduction of error we'll see. We'll also see a great increase in the work that we had to do to get that reduction of error. So if we change h from 0.1 to 0.01, we increase the number of calculations by a factor of 10, but we also get a much more precise description of the true area. If we do the same thing we did before with these 100 intervals, we end up with an area of 0.6614. And if we now compare that to the true answer of 2/3, but it's a little bit unnerving because of the amount of additional calculations we had to do for only gaining one significant digit of precision. If we wanted to gain yet one more significant digit, we would have to yet increase the calculations by another factor of 10. So we would have 1,000 intervals instead of 100. And you can imagine this getting to be somewhat unwieldy, especially if you require that you get 15 significant digits of accuracy on the result. So we are going to be in a situation of far too many calculations and a very slow and wasteful program. So we will leave that at that and come back next time to see how we might be able to gain efficiency without reducing the interval spacing of h too much. So we'll see you next time.